Hey there, and welcome! Today, we're going to gently peel back the curtain on a really cool puzzle. How does a computer actually learn to read the code we write? We're going to be looking at a special kind of tool, a lexical-analyzer generator, which is basically the machine that teaches other machines how to read.
So let's just start with that big question. Have you ever been coding, maybe late at night, and you just kind of pause and think, how does any of this work? How does the computer make sense of all these symbols and letters? Well, it's not magic, and the very first step is actually way more simple and elegant than you might think.
To really get our heads around this, let's use a pretty simple analogy. Just imagine the computer is a kid learning to read its very first words.
You know, just like when we were kids, we didn't start with novels. We started with the alphabet, then we learned to see how letters clump together to form words. A computer does pretty much the exact same thing. Before it can even begin to understand the big picture, the story of a program, it has to be able to pick out the individual words on the page.
Okay, let's look at a super simple line of code. To you and me, the meaning here is crystal clear. But to a computer, at first, this is just noise. It's a jumble of characters. It doesn't see price or 5. It just sees P, then R, then I, and so on.
So the very first job for a compiler, this part is called lexical analysis, is to scan through that raw text and chop it up into meaningful little chunks. It learns to see the group of letters price, the equal symbol, the number 5, and that final semicolon.
And these little chunks, they have a name. They're called tokens. Now here's the really important part. A token isn't just the string of characters, like price. It's the string plus a category. So price becomes an identifier token. The character 5 becomes a number token. This whole process of grouping and categorizing is how the code starts to get some real structure. It's like building up the basic vocabulary.
So the computer needs to go find all these tokens. But how does it know what a valid word or token even looks like in the first place? Well, it doesn't just guess. We have to give it a really precise rulebook to follow.
And you know, this comparison between a human sentence and a line of code, it's not just a cute analogy, it's fundamental. Just like English grammar has rules for what counts as a word, a programming language needs a formal grammar to define its tokens. The problem is basically identical.
And that leads us to the next big question, right? How do we actually write these rules down in a way a computer can perfectly understand? How do you describe the pattern for every possible variable name, or any number someone could ever type?
The answer is this incredibly powerful tool called a regular expression. Now, you've probably bumped into these before. They're basically a super concise language for describing patterns in text. And for someone designing a compiler, they are the absolute perfect tool for the job. They're how you write the rulebook for your language.
Now, don't worry about understanding all the mathy notation here. The big idea is to see how these rules get built. It's like Legos. You start with these tiny, simple pieces. For example, a pattern like A or B or C is a little regular expression that just means match the letter A or the letter B or the letter C. By combining these simple atoms, we can build up rules to describe every single token in a language.
Okay, so we've got our list of rules, all written out as regular expressions. So what now? Do we have to sit down and, by hand, write some crazy complex program to recognize all these patterns? We could, but thankfully there is a much, much smarter way to do this.
Yeah, trying to build one of these lexical analyzers from scratch is a ton of work. It's just so tedious. You have to think about all the edge cases, and making it run fast is a whole other challenge. The code gets messy really quick, and it's just so easy to make little mistakes.
So this is where the pioneers of this stuff asked a brilliant question. What if we could just automate the whole thing? What if we could just write our high-level descriptions, that list of regular expressions, and then feed it to some special tool that would automatically generate all that complicated, low-level code for us?
And that's exactly what a lexical-analyzer generator does. The whole process is just beautiful. First, you define your tokens with regular expressions. Step 2, you feed that file into a generator program. You might have heard of Lex or Flex. And then step 3, the tool just spits out a complete, highly optimized lexical analyzer, usually in a language like C, all ready for you to use.
Just look at this example of a Lex program. This is so much cleaner than trying to write the same logic by hand. You're working at a higher level. You're just describing what the tokens look like, not getting bogged down in the nitty-gritty of how to find them.
It's a huge step up, making things both faster to write and way more likely to be correct.
Now, this whole automated approach brings up a pretty interesting little puzzle. What happens when a piece of text could actually match more than one of our rules? Let's take a look at how the generator deals with this kind of ambiguity.
Okay, so check out the string ifx. Let's imagine our programming language has a keyword if, and it also has a general rule for variable names, identifiers, like ifx. So as the analyzer is scanning along, it sees the letters I and F, and bam, it finds a match for our if keyword rule. So is that it? Is it done? Or should it keep looking? Because if it keeps going, it'll see the x and find that the whole thing, if x, is also a perfectly valid token, a variable name. This is a classic little conflict, and you need a consistent rule to solve it every time.
And the solution they came up with is just so simple and elegant. It's often called the principle of longest substring, but a lot of people just call it the maximum munch rule, which is kind of fun. The rule is simply this: always match the longest possible string you can. Since if x is longer than if, the analyzer chooses if x. Problem solved. It's a simple, predictable rule that just gets rid of the ambiguity.
So as we wrap up, the really crucial thing to take away here is that this whole idea, describing patterns with rules and using them to understand text, it goes so far beyond just building compilers.
I mean, think about it. Every single time a website checks if you've typed in a valid email address, that's almost certainly a regular expression doing the work. When you use find and replace in your text editor, that's pattern matching. Even the syntax highlighting that colors your code while you type, that's powered by a Lexical-Analyzer running in the background. This one fundamental idea is truly everywhere.
And really, that's what's so cool. We started out asking this big question about how software understands software, and the answer begins right here. It might seem like a small technical topic, but it points to this beautiful truth about computing, that so many of our most powerful and complex systems are really just built on a foundation of simple, clear, and elegant rules. It's a nice reminder that even the grandest designs start with just learning how to recognize the smallest words. Thanks for joining me.